Okay, thanks, Jerry, and thanks for inviting me to speak tonight. My name is Patrick Lalonde. I'm the VDC manager for EllisDon Construction. I'm based out of Ottawa, and I look after the projects for the Ottawa region and also the Maritime region. I'll give like a little bit of an overview, sort of what BIM is, and how we see it from the general contractor's perspective. And then I'm going to provide some examples on some neat things that we're using some of these digital technologies on one of our projects in Ottawa. So basically, the construction industry is sort of one of the farthest behind in all other industry sectors. So I like to start off with this graph just to really illustrate how far behind the construction industry is in compared to the manufacturing sector in terms of efficiency in labor and man hours. So the blue line illustrates the efficiency of man hours per person in the construction sector, and the orange line represents the manufacturing sector. So, and we're actually in a downtrend, because as projects get more complicated, the tools we're using are not keeping up with the complexity, and we're losing efficiency on how we execute this work. And another illustration that shows this, a little hard to read the terms on the left there, but those are different industry sectors, and this is a survey done about how the adoption of digital technologies per sector. At the top is the IT sector, second is media, finance and insurance just below that, and the second last row is the construction industry. So we're just above the agriculture and hunting sector in terms of digitization within the industry. So you can really see that that we're really falling behind in compared to all these other sectors. So I like to use the example of the shipbuilding industry, especially being here in Halifax. I'm sure a lot of people can relate to this. But they've adopted these digital tools. They've adopted 3D workflows because it makes sense for this industry to use these technologies, because they're working with very finite amount of space, and the risk is a lot higher, and they can increase their efficiencies, and start prefabricating their components and manufacture these ships in a very efficient way. So basically, we're trying to do is take all these examples and all these workflows from these different sectors and apply it to the construction industry to think more of a manufacturing approach. So as I mentioned, this is an example of how we're digitizing components of the buildings, where we can break them down into smaller chunks, design them. We can fabricate them in digital tools, and then we can construct these components in the exact same way that you would manufacture them in the shipbuilding sector. So a good way to think about BIM is it's basically an evolution of tools that we've been using before in the past. Traditionally, the drafting, AutoCAD came along as a more efficient computer-based version of hand drafting, and now building information modeling is essentially a more advanced version of the CAD-based systems. And so now when we started using, when they started developing these 3D models during the drafting process, we started to realize that there's all these other benefits to having these models. We can start to use them for fabrication, further detailed analysis, coordination. We can pull quantities from them. We can use them to schedule 3D visualizations, and logistics and planning. So it sort of exploded with all these other use cases for these models. So this is an image of what a traditional hand-drawn drawing looks like for HVAC systems in a ceiling space of yesterday. And this is the type of things that we're using today. So it's the same amount of information, but we're using more advanced tools to display that information and manage it. Another good image, I like to use this one because I'm sure some people can relate to the yesterday's image of using these light boxes to do interference checks between multiple subtrades on the job site. So essentially, it would shine the light, they would overlay the drawings, and you could see if the two systems were interfering with each other. So we're doing the exact same thing today on the image on the right, except we're using the 3D models to do the same process. So we're not sort of reinventing the wheel, we're just adapting to the changing times. And another image, like something that you would see on a typical EllisDon job site. We still maintain the paper-based drawing systems, but we also have access to the 3D model, where we can use in conjunction with the paper drawings and the two-dimensional drawings to help us understand the job and to communicate things in the field. And just another example of how we've integrated these digital technologies into our job sites and into our traditional workflows to help us understand the job and to build the job. And another important thing is that like BIM is not it's not a software. It's not Revit. Some people would like to sell it that way, but it's more of a philosophy. It's more of a culture than it is any particular software or thing. So you can't just simply buy it. You have to adopt it. You have to embrace it. You have to learn it. So this other graphic sort of illustrates all the different social and technical components to what BIM is. Starting in the middle there, the 3D CAD. You have three-dimensional virtual objects. And then you can add intelligence to those objects. And then once you have the information, you have to manage that information. And that makes up the technical core of what BIM is. And then you have the social parts, which is synchronous collaboration, everybody working on the same page, coordinated work practices, everybody working towards a common goal. And then you have the institutional and cultural framework, similar to what Duncan was talking about, putting the standards and the different processes in place from the top down. So yeah, just to jump into some technicals here. So there, if anyone familiar with BIM, there's ways of identifying levels of detail in a model. So we use a standard with the LOD on a scale from 100 to 500. So during design, the models don't have much detail, and then through design development, they get more detailed. Into construction, they become more detailed, and fabrication, shop drawing stage, they increase the detail and complexity until final operations and handover, where we can link as-built maintenance information, and they reflect the as-built condition of the model. So primarily in the construction, we work between the 300 and 400 levels of detail of models. So I'm going to use an example from some of the LRT stations on a project that we're working on in Ottawa. It's a $2 billion LRT system with 13 stations. And each station sort of has its own complexity, not so much on the HVAC and electrical side, but more in geometry and finishes. So we've got components of the building that are at an LOD 300. We've got other pieces of the building that are at fabrication level detail. And we're using point cloud data, which could be considered as-built, and integrating all these together. So this is a rendering of the station. It's got glazing with some soffit panels and an elevator. So this represents the design model. And then we can sort of break that down and collect 3D fabrication models of all the structure. And so what we do with that structure is that we take point cloud scans to make sure that all the structure was installed in the correct location. And then once we do that, we can we produce what we call a deviation report. So if any of the steel is deviating beyond 25 mils, we can identify that from this deviation report because that's going to affect the finishes down the road. So once we've collected the point cloud, we've produced a report of any deviations. We have a 3D model of all of the panel components that attaches to the structure. And then we can install each of those pieces piece by piece, and they have very little tolerance. So everything has to line up, or the pieces won't fit. So the basic principle is we start with the design concept, and then we produce fabrication models of the station components. We use the point cloud scan to verify any deviations, and then we can proceed to installing these pieces without having any issues of them fitting on the field. So another example where we're sort of integrating the point clouds with the fabrication models to identify any field errors or any deviations. We can this particular section of the station can be broken down into many different components. And these are all coming from different fabricators, from the design models, from the point clouds. So basically we have the soffit panel fabrication model, the architectural glazing from the design model. We have steel fabrication model, the mullion fabrication model, and as well we have the point cloud scan. So once we can bring all these separate components together, we can start to verify if there's any deviations and correct those deviations before these components get delivered. So just another example of that, just a bit more of a close-up view. We've got the mullions, the glazing, the edge of the concrete can be very clearly defined with the point cloud, and we have about a half an inch gap in between the edge of the concrete and the glazing. So we would go through the station and verify that all the concrete was in the correct tolerance, so we can make minor adjustments to the fabrication models, and then they were delivered to site and installed in the correct positions. So by doing this process, we were able to reduce some schedule time. So basically for the mullions, which are being produced by one contractor and the glazing produced by another contractor, they have to go through the shop drawing, fabrication, and installation process. And then there's a field measurement step that needs to happen before the glazing shop drawings can be completed, and they can be fabricated and installed. So by not taking field measurements and taking all the required measurements from the model, so we were able to reduce that activity, so these two things could happen concurrently, and both of the fabrication and installation could happen at the same time, and ultimately we reduced that amount of schedule. So, you know, the basic principle is essentially starting with the design concept. We take the concepts and carry that into fabrication, where we have our contractors fabricate the pieces of the building and provide us 3D models of that fabrication. And then when those pieces come to site, we install them exactly the way that they've been detailed in the model. You know, and that's the basic principle of what we're doing and what we're trying to do on all our projects. And that's everything. So thank you.